Okay, number 4 is definitely an interesting problem, so let's attempt it. I mean, you could go to the tables and figure out what it is from the tables, but I'll just show you how to integrate it from scratch. Yeah. Right. So we are doing number 4. So we know that the norm is just the integral of, generally speaking, a of x complex conjugate times a of x dx, and then we take the square from minus a, or from a to b, and then we take the square root of that. So this is the norm of a function. Okay. So if I want to apply that on number 4, let me find the norm square. So I will call this I, which is the norm squared. Yeah. Which is just the integral from minus infinity to plus infinity. Now the complex conjugate of this is itself, dx, and so we end up getting for I, let's call this I, I, to be the integral, minus infinity to infinity, e, so now here we get minus x squared dx. Okay, and the question is, how do we integrate that? Well, I could, the same thing, I do this as an x dependent integral with the same exact logic. I can implement this along the y, because if it works on the x, it definitely works on the y, and call it e to the minus y squared dy. Why not? It's just a change of variables. You know? Okay. And then if I multiply these two, I will get, because this will require a change from single integrals to double integrals to work using polar coordinates. It won't work otherwise. Okay, not bad stuff. Yeah. So if I multiply these two here, I will get I squared equals integral from minus infinity to infinity e to the minus x squared dx, integral minus infinity to plus infinity e to the minus y squared dy. And now I could bring those two under one integral. They're iterated integrals. Each one has its own Riemann sum. So I can combine them. Minus infinity to plus infinity, minus infinity to plus infinity, and then these two can come together as e to the minus x squared plus y squared dx dy. So far so good? Or no? Okay, now here it's convenient to use polar coordinates, because in polar coordinates I know that if this is x and this is y and this is angle alpha, I know that r squared is equal to x squared plus y squared. And I know that x is r cosine theta and y is r, or sine alpha, and y is r sine alpha. So I'll do a coordinate transformation from x and y to alpha. And if I do that, I will get, so this is basically dA in Cartesian coordinates. Now in polar coordinates, so here I'm switching to polar coordinates. to evaluate this double integral. Yeah. Uh, well, in polar coordinates, what's the a? If you were to take an area in polar coordinates, like if you were to take a piece of an area, let's say this guy here is dr, and if this angle here is theta, this angle here would be d theta, and if this is r, this would be r d theta. So this shaded area here would have it's somewhat of a rectangle, and the area of that rectangle is just length times width, which is dr times r d theta. So GA becomes r dr d theta. You can think of that little piece as a rectangle. Yeah. And so going back to my integral, I could do the transformation. So now I know that this guy evaluates to r squared. So the integral becomes I squared will equal double integral. We'll get to the bounds in a second. E to the minus r squared, because x squared plus y squared is r squared, and dx dy, which is dA, we said becomes r dr d theta. Okay, now let's look at the bounds. Well, for the bounds, we know that what's going on here, since we have x going from minus infinity to infinity, in other words, the entire plane, and y is the entire plane, that means we have a circle of an infinite radius, which means r will integrate from 0 to infinity. And if we're looping around, regardless of how many times, regardless of where we are on the theta, we can enclose the entire xy plane with a circle by going just from 0 to 2 pi on theta. That makes a complete turn. So these will be your new bounds. Okay, and if I were to, so this is now, it became a straightforward integral. I could take this separately here, the dr one, and I could use u substitution on that. So u is minus r squared, so du is minus 2r dr, which means negative du over 2 is r dr. And so the inside integral became this became we'll change the bounds in a second. This became e to the u du, negative du over 2, so minus du over 2. And let's do the bounds here. So if r is 0, u is 0, you plug it here in this. And if r is infinity, then u is minus infinity. So this goes from 0 to minus infinity. And then there's a d theta, we could just take it inside its own integral. D theta integrates to theta from 0 to pi will just get you to pi. And this guy here, we could just take the minus half out. Integral of e to the u is e to the u from 0 to minus infinity. So continuing here, we will get 2's cancel, minus pi, and then if I plug in the upper bound, I will get e to the minus infinity Or if you want to replace this with t and then take the limit as t goes to infinity, you could get fancy with calculus 2 here, but no reason to. We know that this is 0 minus e to the 0, so this gets you a 1 times minus pi. So finally we get I squared to equal pi. But our integral is not I squared. If you remember, our integral is I. This is what we're after. So we just take the square root of that, which means I equals square root pi. And hence we were able to evaluate that the integral from minus infinity to plus infinity of e to the minus x squared dx is equal to square root pi. And if you remember, okay, so let's box this. This is an important result we were after throughout this question. And if you remember, this was normalization squared, wasn't it? At the beginning of the question, wasn't this the normalization squared? Let's go back and check. Yeah, it was the normalization squared. So this is root pi, or pi to the half. So that means n, the norm. So the norm will equal square root of that. Yeah? Which is, this is acting weird, pi to the 1/4. So this is the norm. And what's the normalized function? The normalized function, like we discussed, the reciprocal of that, so that's just pi to the minus 1/4 times the function that we were trying to normalize. Yes. Normalized function. The reciprocal of this norm is pi to the minus 1/4 times e. We were trying to integrate e to the minus x squared over 2. So this would be the normalized function. You see how you integrate e to the minus x squared? That's how you do it.